Okay, this is, as Martin said, this is one aspect of the EDSAC Replica project, and it is a replica project. So we're starting from a baseline where we haven't got a big donation. We have one existing chassis with no valves in it, and a lot of photographs, and a few circuit diagrams later enhanced during the project. But mostly there's been a lot of interpretation required. A word about the EDSAC architecture, just to give you a quick view, although I won't say much about the machine itself, we'll do that this afternoon. But EDSAC is quite a small machine. It's got about 3,000 valves in it, which comes with a lot of real estate, but it's not very much logic. And it has a main store of about 18,000 bits. Now you can see from that that the store has to be quite compact. In valve technology, it takes about 5 valves to store a single bit, and that means that you can't. You have to have a storage medium in which many bits are stored in a single component. Hence delay storage. One of the only ways you can get kind of density with this few level of components is to arrange that most of the memory is in flight. The other being things like the Williams tube, where they're spread around spatially, but they're still stored in a single component. Right. So the general structure is one in which we have a loop of delay medium, we insert a bit stream into it, it comes out of the delay, is tidied up, reclocked, reshaped, put back in again, and circulates continuously. And this saves us enormously in component power. It does make the logic slightly more complicated because it's necessary to have synchronizing logic to ensure that you pick out bits at the right time in the cycle. But this is much more offset by the saving in the number of bits per, say, storage. We have not very much storage. We have 32 main store units, which are 576 bits, which gives us about 2.2 kilobyte, which isn't a great deal, plus 9 short delay units used for registers and internal state. As a consequence of the store being by time of flight in a delay, the clocking is determined by that delay. So pulses go through the store, they are broadened a little bit by the passage through the store, and then they have to be masked with the clock by anding them to regain a pulse which is in phase with the clock and the right kind of shape. The downside of this is that if the clock drifts for any reason, it's the clock that has to be adjusted, because we've got 32 pieces of hardware which have all been adjusted to be the same delay time. And even if it's the delay unit's fault, that's because of change of temperature that delay has changed, the clock has to track it. You can't have a fixed clock time, push to control clock, because the store will just drift away from it. And I don't fancy going around opening up 32 boxes and tweaking them all a little to get the length right. So you have a procedure. This is coming out of the AND gate, which restores the pulse to its proper shape. And by tweaking the delay length, you can see this is what it's supposed to look like. This is pulse with the envelope breaking into the previous clock period because the delay was too short, and this is conversely too long. Okay, the original machine is a mercury delay line machine. It's a little bit about what we ought to have been emulating in the replica charm. So the delay is determined by the speed of sound through mercury, And the construction was as a series of tubes filled with mercury with quartz crystal drivers and receivers at the ends of the tubes. They're bent up in batteries of 16 tubes, which are massive side girders and end plates, which gave the physical rigidity and stability. And it was these side girders that defined the lengths. The tubes were actually floating in rubber washers so that they weren't an element in the length determination. They just contained mercury. The pulses down the tubes were radio frequency modulated pulses with a little RF burst for each bit. Now, one of the reasons for doing this is having a very short acoustic wavelength. The end crystals have a beamforming effect, so that the beam pulse goes down the tube without ever touching the sides, so you don't get any multi-path effects, and you don't get too much destruction of the bit structures. The original design for these delays comes out of Second World War radar work, actually countermeasures work that was done by a man called Tommy Gold. And in that was a project for providing a countermeasure to the window chaff system, if you've heard of that. Anyway, that's not relevant now, but it meant that the designers of the original machine had an existing working store mechanism. So working, it took them about 2 years to go from the working store that worked in an analog mode for radar to an equivalent digital store. Okay, so we're not using mercury. So what are the pros and cons and why aren't we using mercury? Well, the pro is it's clearly more effective. We would love to do so. It also makes some of the interfacing within the system easier because given that we've got this RF system, a store which is inherently RF based is easier to work with. There are unfortunately quite a lot of cons. The showstopper, in my opinion, is the temperature sensitivity. That we have a temperature window of about ½ degree for the original design before you start getting losing clock phase with the return data. And in a gallery environment, particularly this gallery environment, ½ degree is just not feasible. I should say, eventually, it didn't work in Cambridge either. So after a couple of years, they moved to putting all the mercury tanks into a thermostatically controlled oven. And this picture is a picture of the oven. Everything was in there, and it was all maintained at a fixed temperature. But if we're trying to replicate the machine as it was originally running, it didn't have any of that stuff. Mercury is a pig to work with. The design only works if you get efficient energy transfer between the quartz crystals and the mercury and back again, which implies that the mercury has to wet the quartz, and the quartz crystal has to be impedance matched into the mercury. It doesn't naturally wet. Mercury doesn't naturally wet quartz, so if you just pour mercury in, you tend to get an air film which reflects the RF back, and you get too much loss of energy. So the procedure was to fill the tank with a suitable liquid, originally alcohol and then I think glycol later, which you then displace by pouring in the mercury very slowly, and if you're lucky, the mercury will wet the quartz crystals. You have to be careful also that the back of the quartz crystals do not touch the supporting blocks. These are toughenal blocks, and if there's any trace of oil left on them from machining, you get an oil film and half the energy goes backwards out of the delay line the wrong way. And it stops working. So a lot of instances in the logbooks about tanks just stopping working and having to be overhauled. The mercury degraded progressively. Amalgams. Mercury dissolves any reasonably reactive metal, so it'll take the zinc out of brass. If you ever put a dab of mercury on anything aluminium, it's spectacular. Because aluminium is only stable in a normal environment because of the oxide film on it. And if you put a touch of mercury on, you get an amalgam on a scratch, and the surface of the amalgam does not form a passivating film, and a white whisk of draw that comes up, and within a matter of hours the whole thing is lace. So it's a dodgy material to work with. It dissolved sulfur out of the rubber sealing washers, and after a couple of years had to be redistilled to purify it. So filling was a nasty operation. If you fill too quickly, the mercury runs down the tube and acts like a power driver and takes out the quartz crystals again. So it's dodgy. And it also has to, because you've got to have the two surfaces parallel and flat within one wavelength at 13.1 megs audio, it has to be high precision machine. There are also other things, health and safety. There's about a third of a ton of mercury in the original. And it costs an awful lot as well. So really, it doesn't seem to be on for this environment. Hence, we do something else. If we had gone for the thermostatically controlled oven, that oven had to be kept going 24/7. So that would also be a problem in this environment at night. So we use wire delay lines. This is another well-known technology used commonly from about 1951. Again, it's working on pure delay, so in terms of the principles of the machine, it's a good replica of what it should be. You've got a pure acoustic delay requiring no internal clocking. So it's not, if you wanted to do the same job putting in a solid state memory, for example, like inside the tubes of the tank, you'd have to provide a clock for that. This has no clock. It's just entirely time of flight of the process. Wire delay lines use magnet-restricted transducers, so you put a coil around a suitable strip, generally nickel, and applying a pulse to it changes the length of that strip, and so that generates a sound pulse. At the other end, the sound pulse comes into the region of the field of a biasing magnet, and that generates field fluctuation, which you pick up in a coil, amplify it, take it away. Generally, for the longer delay lines, the practice at the time was to use them in spiral format. This is one of the amount capacities that we've used, so it's a nice model to take. Essence and Marshall's kit. And generally, the common practice was to intertwine two of these to save space and just save filtering by having two wires going around in a close couple. It works better if you make the sound pulse in the wire a torsional pulse. So what naturally comes out of the transducer is a pressure pulse because you change the length. But if you can take two of those in antiphase and use them to twist the end of the wire so that the torsional pulse moves off as a twist all the way down, it's better for this purpose for two reasons. Firstly, it's a bit slower, so you don't need so much wire. Still more than you who have mercury, but less than if you take it directly. And you get less dispersion in the torsional pulse, so you get a cleaner pulse out of the end. Okay, but we want to keep the interface between the main replica of the machine and the store a defensible interface, an interface which is exactly as it was in the original. So so we have plug compatibility. Now that implies that we're going to have the original machine driving with RF pulses, and the nickel delay line is a baseband system, and so we have to demodulate, clean up the pulses as they come out of the wire delay line, and then remodulate them to RF. So there's quite a lot of work to be done there to make the things fit with the same plug interface as the original had. You can see the steps here. The picture on the left is an input pulse of 13.5 megs, followed by the pulse as seen at the driving coil going onto the wire, followed by what comes out, followed by a reconstructed pulse. That last one's to different scales. And you can see that this is essentially an edge-based system, which is actually is a difference from Mercury, which is based on the presence or absence of the carrier, so it's not edge-based at all. Okay, so we want to build some of these momentum delay lines. We're greatly constrained about physical appearance because they're not what was originally there. There are good papers about the principles by which these delay lines operate, but they are missing a lot of detail. And there's a lot more in the written paper about retrieving some of this detail by doing subsidiary experiments. So we're missing, the kind of things we're missing are in the list here. Nickel is a good magnetostricted material, but only if properly annealed and heat treated. So they say that in the papers. How much do you need it? How much work hardening can you afford to have? Actually, a series of bench tests to figure this out. And the picture down the right-hand side is me annealing test tapes by passing a current through them. Variac can turn up to about 20 or 40 volts AC down them. Let them sit there for 10 minutes, that's about right. We didn't know exactly what the composition of the alloy for the torsional wire was. The published papers give a kind of rough cookbook description, but we had to match that with a known existing alloy, and then find out what heat treatment that needed to give the minimum temperature sensitivity. We had to find a procedure for straightening lengths of 3 metre lengths of wire. If you want to get a clean spiral out of it without any kinks or possibly even places where the things touch, you have to start off with a nice straight length. It turns out you have to start with the wire straight, not pre-curved, because bending the wire into a spiral produces a dispersion effect. Having the sound travel in a spiral also produces a dispersion effect, but they're opposite signs. So if you start with a wire which is straight and then curl it up, the dispersion from two causes cancels, which is nice. But it means you've got to find out how to straighten a long piece of wire. It's not easy. So we have a procedure for doing that by, again, passing a current down it and blipping the temperature so it just softens and dropping it again. Magnetic wire field. The transducers are biased by magnetic field. How big a field? Nobody says. They just say, oh, you have a bias magnet. Yeah, kind of. Thanks, guys. So we did a lot of bench tests to experiment and find out what gave the best sensitivity and the best reliability. It turns out as you reduce the amount of the field strength, you get better sensitivity, but up to the point where, but at a certain point, you start getting hysteresis effects, so that the thing becomes unreliable because you've got inherent retained magnetism in the tapes. And we had to find the coil dimensions for which will work at this frequency reliably, which meant a lot of building of temporary test coils, try and give options. Okay, so we end up with transducers for driving the wire. Each transducer has a pair of coils, so you generate a push-pull sound field in the two tapes. So you, to get these coils, start off with a pair of steel wires, which are held in a jig, and a piece of acetate sheet. Okay, so you make up some steel wires and put little collars of PVC, which are actually the insulation from instrument wire, cut a 1mm slice off the insulation of your own favourite instrument wire, thread it onto the metal, and push it sufficiently far into a block against an acetate tab that you end up with this little collar giving you about 0.5 mm to wind the coils into. At the bottom you can just see the PTFE tubing, a piece of the actual wire used for winding the coils, and you can use this as a wand and get them wind them. It works better if you wind the two coils as a pair because they have to go in antiphase, and if you make up coils separately and then mount them, you have to remember which way around they go, so you don't end up reversing one by accident. Having done that, you pop the whole thing in epoxy, so that's a round coils, that's the coils with a blob of epoxy over them. Then you pull the steel wires out, mount this tab onto a printed plastic carrier, which then sits on a pair of rails, and you can move it backwards and forwards to adjust the overall length. Okay, and then the tapes have to be spot welded onto the end of the torsion wire, which is not difficult in principle, but it's a bit fiddly, because if you have even 1/4 mm offset from the end of the wire or the end of the tape, then that extra mass acts as a flywheel and gives you a resonance and broadens the pulses going through the transformer. This is actually our prototype long wire delay. So this is a pair of 76-bit delays with the various electronics to do. These are the RF conversion demodulator pairs for two lines, and these are pulse shapers. And these boxes are then mounted on racking inside wooden boxes, which were the original EDSAC team called coffins, which were the draft screens for their mercury tanks. So at that level, the profile, the visual appearance is the same as the original. As far as we know, this is our concept of how we're going to build the racking with several rack sections and the boxes feed in there and a power supply. None of the remaining photographs show these coffins, so we have to make, we've got a plan outline of it, giving the size, but what did it look like originally we can't say, so we have to make a sensible guess of what a carpenter might do. And then that's the corresponding unit in the gallery, so kitted out, not far from the sign off, expecting. Okay, just a few words at the end about store components, about testing things. One of the messages from starting this from pretty much from the ground up is that you need a whole lot of testing techniques corresponding to all the components you have to fabricate. So here, for example, is a probe coil wound so that it will fit down the 0.7mm bore of the transducers, and let us measure the longitudinal field profile. This is actually bristle off the brush I used to clean down my workbench with 10 turns of coil on the end. And similarly, you want to know that things are going okay when you feed the nickel tapes in and start trying to use them. So this is another probe, this time on a nickel core, so that you can touch that on the tapes and complete a magnetic circuit and pick up a reading of what the field in the tapes is. Useful debugging things. But you need tools at every level. In commissioning these tools, you get a number of different common error causes. So this picture, we have a data pulse that's submitted. That's the main pulse coming out. You get some RF breakthrough. One of our major challenges has been reducing that from enough that it triggers immediate copying from input to output. You get anywhere where there is a mechanical imperfection in the mounting of the wire, you can echo. And if you get a worst case data pulse, all these echoes add up and can produce a pulse which is comparable with the main data pulse. So you have to get the echoes to an absolute minimum. Right, and there's also things that sometimes go wrong with the electronics at the end. Okay, now you need quite fancy test gear to convince yourself it's all working properly. If you start off with you start off with simple low-level pattern tests, so just a simple data generator that generates a few pulses at the right point. But if the story is going to run for long enough to give demonstrations, we need error rates below 1 in 10 to the 10 by the time we're counting the fact that there are multiple units. To do that, a fairly fancy testing box based on a field programmable gate array system, which lets us do lots of high precision tests timing without scanning errors and so on. I can talk about that this afternoon if you want to know more about it. But it lets us set up random patterns and measure measure error rates over a period and adjust things to the minimum error rate. And just as a closing thing, we aim to move on to elaborate that piece of test kit. At the moment, it tests individual memory test units, and by reworking the interface slightly, we can move it to test complete rack assemblies of 8 units and their adjustments, and then into the complete memory subsystem, and we can use that to check the operation of the machine, of the storage component of the machine during its normal operation. Okay, I'll skip that. And those are just saying the obvious things about keeping visual fidelity and as far as we can, and maintaining interfaces and providing enough storing tools to do all the commissioning. Okay, I'll stop there. I'm sorry, we lost a bit of time there. Not even a map and model. Thanks so much.